Hello everyone, good morning. I think I'm audible, right? Thanks, welcome. So this is 12th lecture of vector analysis. So there is a new playlist called Vector Analysis 2.0 in the playlist. So if you have gone through that playlist, I think I have completed that divergence, curl, gradient concept, and then we have started line integral, surface integral, and volume integral. That also we have completed. After that, we have completed Green's theorem also. So still we have two more theorems left. One is Gauss divergence theorem. The other is Stokes theorem. So we'll complete these two. The syllabus will be completed, right? So if you haven't watched those previous 11 videos, go through that. This is lecture number 12. This is lecture number 12. So if you haven't watched all the previous 11 videos, so go through that, right? Okay. So in this class, we will start Gauss divergence theorem. So I think if this will go for 2 or 3 classes maximum, then Stokes theorem 2 classes maximum, then syllabus will be completed. Then we will do some practice questions or previous year's questions later that. Okay. So first we will write the statement of Gauss divergence theorem. So I hope everyone had idea about line integral, surface integral, and volume integral, right? So just go through those notes so that you will. I have already completed all those, but you might have forgotten. So please go through the notes also. Okay. So what this theorem says is, so I'll just state the theorem, then we will do 3 problems in this class, right? All 3 problems are very, very important. This topic is very, very important. Surely you can expect one question from Gauss divergence theorem. So from these 3 theorems, you will have 2 questions. Green's, Gauss divergence, Stokes, right? Okay. So first I will write down the statement, then we will take a problem and then we will verify the theorems, right? So what this theorem says is the surface integral the surface integral of the normal component surface integral of the normal component the surface integral of normal component of a vector point function of vector point function f. So we have a vector point function f taken over a closed surface s. Just write on a statement and I explain. Taken over a closed surface taken over a closed surface s enclosing a volume v is equal to the volume of the integral equal to the volume of the integral of divergence of f taken throughout the volume taken throughout the volume bounded by S. Right, so this is what Gauss divergence theorem states. So what it says is, so we have a surface integral. So surface integral is double integral over S f vector dot n cap ds. That is the formula for surface integral. So what it's saying is the surface integral of the normal component of a vector point function taken over a closed surface S enclosing a volume V. So I'm going to combine these first three lines up to this. I'm going to write this mathematically. So what it says is the surface integral of f vector dot n cap ds taken over the surface is equal to the volume integral is equal to the volume integral is equal to the volume of the integral of divergence of f del dot f taken throughout the volume bounded by s. Is it clear? This is what this is. So what this says is, if you have a vector point function, right? If you have a vector point function f, the surface integral of the normal n cap is normal, right? The surface integral of the normal component of a vector point function taken over a closed surface enclosing a volume V is equal to the volume of the integral of divergence of f taken throughout the volume bounded by s. This is what Gauss divergence theorem says. So you just by heart this theorem, right? Then you will work out the problem. Then it will be easy for you to understand. So what it says is surface integral is equal to volume integral taken over divergence of f. This is surface integral. This is volume integral. So surface integral taken over this surface is same as volume integral of del dot f. That is divergence of f. This what Gauss divergence theorem says, right? Okay. Now we will do some problems based on this. It will be easy for you to follow. So the question will be like, verify Gauss divergence theorem. Verify means we need to show that the surface integral and volume integral both are same by applying here. Right? Here the volume integral is taken over divergence of f. So the question will be like, verify Gauss divergence theorem. They will give a vector point function and they will give a surface also. So usually in exam point of view, you will have only four surfaces. One is cube, that is cube and cuboid. Second will be cylinder. Third is sphere. Fourth is hemisphere. So they will play only with these four shapes: cube and cuboid, cylinder, sphere, hemisphere. So maximum and cone also, right? Cone also. So they will play only with these five shapes: cube and cuboid, cylinder, sphere, hemisphere, and cubes. So they will play only with these four shapes. So we need to verify Gauss divergence theorem. They will give any one of these five shapes, and they will make some constraint also, right? Okay. Is the video is clear or is there any lag? Okay. So in exam point of view, they will give any of the shapes like cube. Okay, thank you. So we'll do some problems straight away, right? Problem one. Verify verify Gauss divergence theorem You have already explained what is volume integral, what is surface integral in the previous classes, right? So don't think that I've simply changed the statement. I've already explained all those in the previous classes. So verify Gauss divergence theorem for they are given f. So they are given the vector find function f is x square minus yz I vector plus y square minus zx j vector plus z square minus xy k vector taken over a rectangular parallelepiped taken over a rectangular parallelepiped and they are given the bounds for x, y and z. This is a parallelepiped, right? So it can be cuboid or cube, but it is a cuboid, right? It is a cuboid. So they are given, we need to verify Gauss divergence theorem. So we know F and the constraint here is, the solid here is cuboid, right? Okay. So what we need to do is we need to verify that. So what we need to show, so to show double integral over a, sorry, double integral over s f vector dot n cap ds is same as triple integral over v del dot f vector dv, right? This is divergence of f. Del dot f is divergence of f, del dot f into dv. Now first what we will do is we will draw the diagram, then only we can do the problem, right? First we will draw the diagram, then only we can do the problem. Okay, so they are given. So first we will draw a parallelepiped, right? Very, very important. Okay, just a minute. So we will draw. So we have a parallelepiped, right? We have a parallelepiped. This is very, very important. If you understand this diagram, that will be easy for you to follow. Let us call this as x-axis, call this as y-axis, and call this as z-axis. Let this be origin, right? Let this be origin. So let us mark the vertices. Let us call this as A, call this as B, call this as C, call this as D, E, F, G. Right? So we have named the all vertices. See, cuboid or cube, this will have six faces, right? Front, back, left, right, up, down. So you can visualize there are six faces here. Front, back, left, right, up, and down. So there are six faces in cuboid, and there will be 12 sides that you all know. So first they have given that the rectangular pivot is taken over, x varies from 0 to a, y varies from 0 to b, z varies from 0 to c. So here this is origin 0 comma 0 comma 0. So here we are moving in x, sorry, y, right? Here we are moving in y. So we are moving in y. So we are moving in y, and y, the maximum distance is b. So we are moving b units to the y. This point will be 0 comma b comma 0. Is it clear? And similarly, from origin we are moving through z axis. Z maximum is c. So 0 comma 0 comma c. XY will not change, right? From here we are moving only through z axis, and here From origin, we are moving we are moving in x-axis. How much units? A units. This point will be a comma 0 comma 0, right? And to know b from 0 comma 0, from 0 comma b comma 0, we are moving z axis, and we know z. This length is c. This length is b. This length is a, right? Because z varies from 0 to c, y varies from 0 to b, x varies from 0 to a. So from 0 comma b comma 0, we are moving z. We are moving c units in z axis. So this will be 0 comma b comma c, right? Yes. And to know f from a, we are moving a units in x axis, because if I come here, it is x axis. So we are moving a units in x axis. It will be a comma b comma 0. B0 will remain same. We are moving only in x axis from a to this point. From a comma b comma 0, we are moving in z axis. We know z axis is c units. This point will be a comma b comma c, right? To know, yes, I think you have completed all points, right? So a, yes. So now what is d? Now a comma 0 comma 0, we are moving in z axis. So a comma 0 comma c. If the vertices are clear, the vertices naming is very important. I think the vertices namings are clear, right? Yes. Now first, what we will do is we will evaluate this triple integral. That is very easy, right? Now, first, what we will do is we will evaluate the triple integral. So, what is triple integral? Triple integral over del dot f vector dv. So, dv is in Cartesian form, it is dx, dy, dz, right? Now, what is del dot f? So, what is del dot f? It is nothing but divergence of f. So if f is this, del dot f is dou by dou x of this, dou by dou y of this, dou by dou z of that. This will be triple integral. Okay, so let me recall all this, right? So del is gradient, dou by dou x of I vector, dou by dou y of j vector, dou by dou z of k vector. This is what del, right? Gradient dot f. Now what is f? They have given x square minus yz I vector plus y square minus zx j vector plus z square minus xy k vector. Now you have to make a dot product with this. You have to make a dot product with this. So dou by dou x of this. So this will be triple integral. Dou by dou x of this. It will be 2x, right? So you just have to partially differentiate this with respect to x. So you just make a dot product. You have to multiply corresponding I component, j component, k component. So this will be 2x. Dou by dou y of this is 2y. This will be 0. Dou by dou z will be 2z. And instead of dv, I am writing dx, dy, dz. Now for triple integral, we know x varies from 0 to a, y varies from 0 to b, z varies from 0 to c. So here x varies from 0 to a, dy, y varies from 0 to b, z varies from 0 to c. So you just evaluate this triple integral, you can get this answer. This triple integral evaluation is very easy when compared to double integral. So you just take 2 outside. There is 2 outside. So integration of 0 to c, integration of 0 to b. So you just integrate this, integrate x plus y plus z with dx. So x dx is x square by 2 plus yx plus zx 0 to a dy dz, right? I have just integrated with respect to z. So I have just taken 2 outside. So you have x plus y plus z. So x dx is x square by 2, y dx. So y dx is y is constant, integration of dx is x. So we'll have yx, z dx. You can take z outside, z into integration of dx, which is zx. Now you apply x limit. So if I apply x to be equal to a, see remember this x varies from 0 to a, this is y varies from 0 to b, this is z varies from 0 to c, this is y varies from. This y varies from 0 to b, this is x varies from 0 to a. Now if I apply x to be equal to a, so we will have 2 times integration of 0 to c, integration of 0 to b. So if I apply upper limit minus lower limit, so a square by 2, a square by 2 plus ay plus az, a square by 2 plus ay plus az, dy dz. Now integrate with respect to y. So we will have, so here there is no y term, so it will be a square by 2 is constant, integration of dy is y. Here we will have y dy is y square by 2, and az is constant, sorry, az is constant, and integration of dy is y. Y varies from 0 to b, and we will have dz. So this will be 2 times integration of 0 to c. So apply upper limit y. So we will have a square b by 2 plus ab square by 2 plus ab into z. So lower limit will be 0 because 0, 0, 0. Lower will be 0. So upper limit is a square b by 2, ab square by 2, ab z. Now integrate with respect to z. So a square b by 2 is constant. Integration of dz is z. And again ab square by 2 is constant. Integration of dz is z plus ab. Integration of z is z square by 2. Now you apply upper limit minus lower limit. So 2 into a square bc by 2, a b square c by 2 plus a b c square by 2. So I can cancel this 2, 2, 2 with this by taking 2 outside. Now if I take a b c outside, we will have a plus b plus c. Yes or no? I'm just taking a b c common. So we will have a plus b plus c. So a b c into a plus b plus c is the volume integral, right? ABC into a plus b plus c. So we have found the triple integral del dot f dv. Now we need to find the surface integral, which is very very important. Now we need to find double integral over s f vector dot m cap ds. Now to find, so double integral over s f vector dot n cap ds. Right, now finding n cap is not that easy, right? Finding n cap is not that easy, you need some practice. So I'll explain how to find n cap. Now for surface integral we have 6 surfaces now, right? We have 6 surfaces. What are those 6 surfaces? So s1 is your front surface, s2 is your back surface, s3 is your right surface, s4 is your left surface, s5 is your up surface, s6 is your down surface. So to evaluate surface integral, you need to evaluate that 6 integrals, right? We need to evaluate that 6 integrals. So this is same as double integral over s1, double integral over s2, see, you will have f dot n cap everywhere. I'm not writing this. S3, double integral over s4, double integral over s5, double integral over s6. So for parallelepiped cuboid, you will have 6 surfaces, right? 6 faces. So you need to find the double integral for each of the surfaces. So for each of the surfaces, n cap will vary, ds will vary, and we need to apply the corresponding limits, right? We need to apply the corresponding limits. It's a very very important point here. Now first what we will do is we will evaluate the front face, right? We will evaluate front face, which is s1, and we will evaluate back face, which is s2. So back face, which is s2, right? We will take front back, and then left right, and then we will take up down. Now we need to evaluate double integral over s f vector dot n cap ds. This is what we need to evaluate, right? Okay. Now for this surface, we need to find n cap. We need to find n cap, and then we need to find ds. And similarly for this surface also, see, we are evaluating this s1, and for again for this surface, we need to evaluate a double integral over s2 f vector dot n cap ds. Now this will have some n cap, and this will have some ds. What is n cap? N cap is the unit normal vector perpendicular to that surface. N cap is the unit normal vector. So that normal means that is perpendicular to the surface, right? Okay. Now you take the front face, right? Now you take the front face. For front face and back face, how to find n cap and ds? How to find n cap and ds? Okay. See, let me take one cube and then I will explain you. For all the problems based on cubes, cuboid, you will have only this idea, right? You can memorize this also, but you can memorize later, but you have to know why n cap and ds. See, I have a cube, right? I have a cube now. I have a cube, and this is my front face S1, right? I think it is visible in camera. This is my front face S1, and this is my back face S2, right? So S1, S2, so left, right. So S3, S4, and then up is S5, down is S6. So we have six surfaces. Now first I'm going to find the uh, S1. First I'm finding the double integral over S1. Right? I think it will be visible in camera. Okay, so I think it will be visible now. See, this is my S1 and this is S1, back is S2, right? So we have front and then back, and then we have right and then left, and up is S5, down is S6. So let us take this front face S1. Here marking this as x-axis, y-axis, and this is z-axis, right? X-axis, y-axis, this is z-axis. Now we have a face S1, right? We have face S1. Now let us make a unit normal vector that is perpendicular to S1. So this pen is a normal vector that is perpendicular to S1. Yes or no? This pen is a normal vector perpendicular to S1. Now you can see, now you can see this unit vector is parallel to, is same as x-axis. Yes or no? This is x-axis. This is x-axis. So you can see this n cap is same as the x-axis. Yes or no? See, I'm just drawing a unit normal vector. See, unit normal is magnitude is 1. So just draw a normal vector that is perpendicular to S1. Now you can see if I rotate this n cap, this vector is same as the x-axis. Yes or no? So you just extend the x-axis, you will have this. So for S1, your n cap is I vector, because for x-axis we will have I vector as component, and for y we will have j vector, and for z we will have k vector. So for S1, your it is a perpendicular vector. Now if I rotate this, you can see this x-axis is same as this unit vector. So your n cap will be I vector, right? See, if you understand this one problem, you can do any problem based on parallelepiped. And you can see in this surface x is fixed. Only thing is we are varying over y and z, because this is y axis, this is z axis. So we are varying over y z. So where we are varying over y z. So it will be dy dz. Is it clear? We are varying over y and z, right? Okay. Now similarly, let us take a back face. I'm taking a back face S2. Right, I'm making a back face S2. So we know front face, your n cap is same as x-axis. Now let us take a back face now, S2. Again you draw a unit normal vector, right? Now you can see again this is same as x-axis, but it is in opposite direction. Is it clear? It is in opposite direction. Yes or no? So for S2, again it is x-axis, but it is in opposite direction. So your n cap will be minus I vector. Again, we are varying only over dy and dz. For back also, we are varying here only. So which is y, this z. So your ds will be dy dz. Is these two are clear? I think these two will be clear, right? See, always this will happen. For front side, your n cap will always be I, and your ds will always be dy dz. And for back side, n cap will always be minus I, and ds will always be dy dz. See, here we are varying y z. So we need to find the y limits also. Yes or no? We need to find the limits for y and z. We need to find the limits for y and z. Now easily, right? So what is the limit for y and z? Y varies from 0 to b. Z varies from 0 to C. Yes or no? That is given right. Z varies from 0 to C. See, for front face, we have S1. So here, Y is varying from 0 to B, Z varying from 0 to C. X is fixed here because there is no X here, right? X is fixed. So X is fixed means X is equal to A. Because it is fixed at X is equal to A. Is it clear? See, we are moving only in YZ. X is always fixed. What is X? X is always A, right? X is always A. So this means YZ it is varying. Okay. If not, I have found Y, Z, X limits like this. If not, you just take the front face. You just take the front face. This is the front face, right? So what is the front face? This is the front face. This is the front face. Now you can see for the front face, all the X coordinates are same. A. That means you take X is equal to A, and you can see for X phase, Y varies, this is Y varies from 0 to B, and you can see Z varies from 0 to C. You can also take like that. To take a front face, see which coordinate is fixed. So X is equal to A, and you can see Y varies from 0 to B. So you can see it is 0, it is B, and Z varies from 0 to C. You can also take like that if you are not comfortable with diagram. So you take a front face, you see which is fixed, and you see which is varying from where to where. From where to where. Okay. So this is a method. See, for every phase, you need to find these three things first: n cap, ds, and limits of x, y, z. So how to find n cap? N cap is always I vector for front side, that I have already explained why. And for back side, n cap will always be minus I, that I already explained. And this is fixed for all, whatever cube they give. This n cap ds will not vary. Only thing will vary is the limits will vary. Suppose if they say x varies from 0 to 1, you will take you just take that number. Here they have said y varies from 0 to b and z varies from 0 to c. That's why I have taken those limits. The limits may vary for all the problem, but this n cap and ds will not vary. But this n cap and ds will not vary. Okay. Now after finding these three, and again here also, what is ds is dy dz. Y varies from 0 to b, z varies from 0 to c, and x is a. Here also x is a. Why? You just take the back face now. So you just take the back face now. So what is back face? This is the back face, right? Sorry, front, back. Sorry. Now for back face, you can see x is 0. Sorry. For back face, x is 0. X is 0. Y varies from, you can see, you just take the back face, you can see all the coordinates of x is 0, right? And z varies from 0 to c, y varies from 0 to c. 0 to c. Is it clear? So for front face, x is a is fixed, and y and z are varying. For back face, x is 0 and y and z are varying. So these are the three things first you need to find for this. Okay, now we will do this. Now we will do it. Now we need to find double integral over S1 f vector dot n cap. So already we know f vector. So f vector dot n cap. So I think I don't want to do this. See f vector dot I, because n cap is I. So what is f dot I? So if you make a dot product f with I, you will have only x square minus yz. Yes or no? See, you just make a dot product of this with I vector. So x square minus yz, and these two will be 0 because there is no j and k. Make a dot product, it will be 0. So you will have x square minus yz. Yes or no? X square minus yz. This will be the f vector dot n cap, and ds is dy dz, and y varies from 0 to b, z varies from 0 to c. This is the S1 surface, right? So you just now it is now x is a here. So 0 to c, 0 to b, a square minus yz dz. So 0 to c, integrate with respect to dy. So this will be a square y minus z into y square by 2, 0 to b dz. Now this will be integration of a square b minus, sorry, integration of y does it y square by 2. Now apply upper limit minus lower limit. So here we will have here you will have a square b minus zb square by 2 dz, right? Now you just integrate with respect to z and apply the upper and lower limit. So you will have 0 to c. So this will be a square bc, right? Because a square b integration of dz is z, upper limit is c. So you will have a square bc. Here you will have minus b square by 2, minus b square by 2. Z dz is z square by 2. So z square by 2 upper limit is c square by 2. Right, so a square bc minus b square c square by 4. This will be the S1 surface. This is the surface of S1. Now similarly you find S2. So this is double integral over S f vector dot n cap. So this will be minus of x square minus y z dy dz. And we know x is 0, so this will get vanished. So y varies from 0 to b, z varies from 0 to c. So integrate with respect to y. So that will be constant. Integration of y is y square by 2, 0 to b dz. So this will be b square by 2, right? B square by 2 outside. Integration of z dz is z square by 2, 0 to c. So you will have b square c square by 4. So this is your S2. So S1 is a square bc minus b square c square by 4, and S2 is b square c square by 4. Is it clear? So we have found two surfaces now, S1 and S2. Now similarly, we need to find S3 and S4. So that means right and left. So we'll take a right surface now. So we'll take right, so which is S3, and we'll take left, which is S4. So we need to find double integral over S3 f vector dot n cap ds. And similarly, you need to find double integral over S3 f vector dot n cap ds. Now we need to find n cap, we need to find dz, and we need to find limits also. And here also we need to find n cap, we need to find ds, we need to find limits also. Now let us take a right surface, right? So we have S1, front, back, and then left, right, up, down, right? Let us take the right. So right is here, S3, which is on the x-axis. Now you take a vector that is perpendicular to S3. Now you can see this is same as y-axis. Yes or no? See, this is y-axis. So your this vector is nothing but j vector, j cap, right? N cap is nothing but j vector. So I'm taking a vector perpendicular to S3 because this is a unit normal vector. N cap is a unit normal vector. Normal vector means we have to take a vector that is perpendicular to S3. So your S1 will be, sorry, your N cap will be y axis, positive y axis, which is nothing but j vector. So your N cap is j vector. And similarly, and here you are varying over x and z, yes or no? So we are in S3, so this is x, this is z. So we are varying over x and z in S3. So ds will be dx dz, dx dz, right? And similarly, if you take a left surface, take a left surface S4, this is your unit normal vector, and you can see it is nothing but opposite of y, opposite of y, so it will be minus j vector, minus j vector, and here also we are varying over x and z. So this is clear, right? So for left and right, your n cap j cap will be I j vector minus j vector, and which is fixed here. You just take a right surface. You just take a right surface. Now we can see for the right surface, this is the right surface, right? This right. For right surface, y is equal to b is fixed. Yes or no? Yb, 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 yb. And x and z are varying. Yes or no? You can see from these four coordinates, y is b everywhere. So y is b, x varies from 0 to a, z varies from 0 to c. This is what? See, you can always refer diagram to find limits. It will be easy for you. So y is b here, y is fixed, x varies from 0 to a, z varies from z varies from 0 to c. See, whatever you have, dx, dz, this will only be vary. X and z will only vary. This is a hint for you. And here also, for the left surface, on the left surface, you can see this is a left surface, right? Now for left surface, this is the left surface. Y is always 0. For all the four coordinates, y is 0. X and z are varying. Y is 0. X and z are varying. So y is 0. Y is 0. X and z are varying. So and we know x varies from 0 to a from the question. 0 to a, and y, sorry, z varies from 0 to c. Now we are equipped to do this problem. So integration of S3. What is f dot n? So f vector already given the question. You make a dot product with j vector. So if you make a dot product with j vector, you will only have this thing y square minus zx. Other two will be 0. So y square minus zx. Y square minus zx. And ds is dx dz, and x varies from 0 to a, z varies from 0 to c, and we know y is b. So the integration of 0 to c, integration of 0 to a, b square minus xz dx dz. So integrate first with respect to x, will be b square x minus x square by 2 z. Right, now integration 0 to a dz. So upper limit minus lower limit. So this will be a square b minus a square z by 2 dz, 0 to c. Now integrate and substitute upper limit minus lower limit. So a square b is constant. Integration of dz is z. Upper limit is c. Here a square by 2. Integration of z dz is z square by 2. So upper limit is c square by 2. So a square bc minus a square c square by 4 is your S3 surface. Now similarly you find S4. So F vector dot n cap. So minus j. So minus of y square minus zx dx dz. X varies from 0 to a. Z varies from 0 to c. And we know y is 0. So this will get cancelled. So we will have integration of xz dx dz. So x varies from 0 to a. Y varies from 0 to, sorry, z varies from 0 to c. So this will be integration of 0 to c x square by 2 0 to a dz. So this will be a square by 2. Integration of z dz is z square by 2, which is c square by 2. So we will have a square c square by 4 is your a square c square by 4 is, see, just since it is the first problem, it is taking time. But if you know it is cube or cuboid, this will always will not vary. N cap ds will not vary. Only thing is limits will vary depending upon the question. Whatever limit they give, it will vary. Is it clear up to now? Now we will move on to up and down. So we'll move on to up and down. So for up surface, that is S phi. So we need to find double integral over S phi f vector dot n cap ds. We need to find n cap, we need to find ds, and we need to find limits also. And similarly for down also. So for down it is S6. We need to find S6 f vector dot n cap ds. Now we will find n cap, we will find ds. Right? Now let us take a up surface. See, we have we have S1, S2, S3, and 4. Right? I'm taking a up surface. So up surface is S5. Right? So we have y, we have x, we have z axis, and I'm taking a vector that is perpendicular to S5. Now we can see this is same as the z axis. Yes or no? This is same as the z-axis. So your unit normal vector is nothing but your z-axis, which is nothing but a k vector. This is nothing but a k vector. You can see this is your S5. I'm taking a unit normal vector perpendicular to this, and you can, and if I rotate this, you can see. If I rotate this, you can see this z-axis is your lies along the z-axis, or it can be parallel also, right? It can be parallel to z-axis also, but your unit vector will not change. Your n cap will be k vector, and it will vary over dx and dy only, because we are in S5. So S5 you can see it is S5. So y and z only we are varying here. So this is y, this is z, this is your surface S5. So we are varying over y and z. So it will be dx dy. And similarly here also n cap will be minus k vector, and it will be dx dy. So you just by heart from now on that whenever you have left to right, whenever you have front to back, n cap is I minus I, and for right and left j minus j, and for up and down k minus k, and ds will vary. So if you have k means xy dx dy, just remember like that. Now for up, z will be c, x varies from 0 to b, 0 to a, x varies from 0 to a, y varies from 0 to b. And here where z will be 0, x varies from 0 to a, y varies from 0 to b. See, you can easily find out why z is a, z is c. See, you can see for the up, this is your up, right? This is your up, and for this you can see z is c, uh, c. So zc is fixed, and you can see x varying, right? X varies from 0 to a, y varies from 0 to b, and for down z will always be 0 is fixed, x and y are varying. So therefore f vector dot n cap ds, this will be double integral over s5. Now n cap is k vector. If you make a dot product with f dot k, make a dot product with f dot k, so dot k z square minus xy, this will be z square minus xy, and ds is dx dy. And we know x varies from 0 to a, y varies from 0 to b, and we know z is c, this will be 0 to b, 0 to a, c square minus xy dx dy. So integrate this. So 0 to b, c square is constant. Integration of dx is x. Upper limit is a. And here y is constant. Integration of x dx is x square by 2. Upper limit is a square by 2 dy. Now integrate with respect to y. So ac square is constant. Integration of dy is y. Upper limit is b. And here we have a square by 2. So integration of y dy is y square by 2. So we will have b square by 2. So this is nothing but ab c square minus a square b square by. So similarly you find this. So it will be s6 f vector dot n cap will be minus of z square minus xy dx dy. And we know z is 0. So integration of xy dx dy. X varies from 0 to a, y varies from 0 to b. So this will be 0 to b. So y is constant. Integration of x is x square by 2. Upper limit is a square by 2 dy. And here a square by 2 is constant. A square by 2 is constant. Integration of y dy is y square by 2. Upper limit is b. We will have b square by 2. So you have a square b square by 4. So we have found the double integral of all the six spaces, and we know that double integral over s f vector dot n cap ds. So therefore, double integral over s f vector dot n cap ds is same as double integral over s1 double integral over s2 plus double integral over the surface s3 plus double integral over the surface s4 double integral over the surface s5 plus double integral over the surface s6. So we have found all the answers, and for s1 it is a square bc a square bc minus b square c square by 4. A square bc a square bc a square bc a square bc minus b square c square by 4. This is what we have, right? A square bc a square bc minus b square c square by 4, and this is plus b square c square by 4 plus b square c square by 4. This is your left, this is your sorry, this is your s1, this is your s2. Now s3 plus s4. Now s3 is a square bc a square bc b b square ab. Sorry, I think I made a mistake here. So if you apply the upper limit, it will be ab square, not a square b. So it is ab square. This will be ab square is constant. Ab square c. Sorry, ab square c. So ab square c ab square c minus a square ab square c minus a square c square by 4. Or no? A b square c minus a square c square by 4. Here you have plus a square c square by 4. Now your s5. So s5 is abc square minus a square b square by 4 plus your s6 is a square b square by 4, right? A square b square by 4. Now these two will get cancelled. These two will get cancelled. These two will get cancelled. So if I take ABC common from this, and this, you will have A plus B plus C. So which is same as the volume integral. Which is same as the volume integral, which we already found, right? So we have found double integral over S F vector dot n cap ds is ABC A plus B plus C, and we have already found the volume integral, which is again ABC A plus B plus C, right? Volume integral is very easy. Just you find del dot f dv, just find divergence for f and make a dot product, that is del dot f dv. So dv, so dv is dx dy dz. Just apply the limits, you will get the answer. Just evaluate this triple integral. It turns out to be, let's call this as 1 and call this as 2. So from 1 and 2, Gauss theorem is verified. See, from now on, you just remember that your front face is n cap is I, and for back n cap is minus I, left n cap is j, for right n cap is minus j, and for up n cap is k, and for down n cap is minus k. And ds, and just find the limits: x varies, y varies, z varies. Then you can easily do the problem. You just need to add up all 6 phases. Is it clear? Can you do one more problem based on this? Is it clear, right? Okay, so we'll do one more problem based on this, based on the same cube. To verify Gauss divergence theorem, to verify Gauss divergence theorem, verify Gauss divergence theorem or f vector is 2x minus z I vector plus x square y j vector minus x z square k vector taken over a region, bounded by taken over a region bounded by x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0. It is same as parallelepiped, right? So don't confuse. This is same as the previous problem. It is bounded by x varies from 0 to 1, y varies from 0 to 1, z varies from 0 to 1 again. This is same as the previous problem. In the previous problem, they have given that x varies from 0 to a, y varies from 0 to b, z varies from 0 to c. Here, all are varying from 0 to 1 only. So it means it is easy when compared to the previous problem. Okay. So we need to verify Gauss Divergence theorem. So double integral over S f vector dot n cap ds is same as triple integral over v del dot f vector dv. Right? Triple integral over v del dot f dv. Now we will draw the diagram. Diagram is easy. So we have this is our x axis, y axis, and z axis. This is the origin, right? Let's call this as A, call this as B, call this as C, call this as D, call this as E, F, and then G. Right? This is origin 0, comma 0, comma 0. Now here you can see everything is bounded by 1 only. X varies from 0 to 1, Y varies from 0 to 1, Z also varies from 0 to 1. So we are moving 1 units to the Y axis. It will be 0, comma 1, comma 0. If you are moving B units in Y means it will be 0, comma B, comma 0. But here we are moving only 1 in Y. And from 0, comma 1, comma 0 we are moving in Z. It will be 0, comma 1, comma 1. From 0, comma 1, comma 0, we are moving 1 units in x-axis. So 1, comma 1, comma 0. And from 0, comma 0, comma 0, we are moving 1 units in x-axis. So it will be 1, comma 0, comma 0. Right? Okay. And from From 0 comma 0 comma 0 we are moving 1 units in z. D will be from 1 0 0 we are moving 1 units up, so it will be 1 comma 0 comma 1, and E will be 1 comma 1 comma 1. So one from 1 comma 1 comma 1 we are moving this, right? Okay. So from here we are moving x units. So 1 unit we are moving in x. So 1 0 0 we are moving is 1 unit z. So 0 0 1, and from here we are moving. Sorry, from here you always take positive direction, right? Then only it is easy to plot. So from here positive z. So 1 0 will remain as it is from 0 to 1, and 0 1 0 positive z. So 0 1 will remain as it is from 0 to 1, right? And again positive x. So 1 1 0. From here it is you always use positive x y z, so it will be easy to plot. It will be easy to plot. Okay. Now we will find triple integral over. Now we will find triple integral over v del dot f vector dv. So what is del dot f? You just have to take a divergence for this. So del dot f. So what is del? Del is dou by dou x, dou by dou x of I vector gradient, dou by dou y of j vector plus dou by dou z of k vector dot f. So f is 2x minus z I vector plus x square y j vector minus x z square k vector dv. So this will be dv is dx dy dz, right? So dou by dou x of this 2, dou by dou y of this. What is dou by dou y of x square y? So it is plus x square. Now what is dou by dou z of this? So dou by dou z of this is minus x is constant. So minus 2xz dx dy dz. X varies from 0 to 1, y varies from 0 to 1, z also varies from 0 to 1. Is it clear? So we will have 2 times, you will have 2 times, sorry, 2 plus x square minus x square z. So dou by dou x, dou by dou y. So dou by dou x, I think question is correct, right? 2x minus z. Just a minute, I'll just check the question once again. Question is wrong, then everything will be problem for me. Just a minute. So yes, 2 plus x square minus 2xz. Yes, correct. Now we will integrate this over dx dy dz. So that is we need to triple integrate 2 plus x square minus 2xz. So dx dy dz, and x varies from 0 to 1, y varies from 0. In the previous problem we have written 0 to a, 0 to b, 0 to c, but here everything is 0 to c, 0 to 1 only. So you differentiate with respect to, integrate with respect to x. So 2x plus x cube by 3, 2z x square by 2. X varies from 0 to 1. X varies from 0 to 1, dy dz. So 0 to 1, 0 to 1. So 2 plus 1 by 3 minus 2z by 2. So I'm just substituting upper limit minus lower limit. So upper limit is 1. So 2 plus 1 by 3 minus 2z by 2. This is integration of 0 to 1, integration of 0 to 1. This is 7 by 3 minus z dy dz. Now integrate with respect to y. So 7y by 3 minus zy, again 0 to 1 dz. So integration of 0 to 1. So this will be 7 by 3 minus z dz, right? 7 by 3. So when you put y to be 1, 7 by 3 minus z dz. So again integrate with respect to z. So 7 by 3 minus z square by 2, 0 to 1 will be 7 by 3 minus 1 by 2. So if we take LCM, 14 minus 3 by 6. So 11 by 6 square units, sorry, cubic units. So 11 by 6 is your triple integral, right? 11 by 6 is your triple integral. The previous problem we have got ABC into A plus B plus C. So here we have 11 by 6. See, you take the previous problem, we have ABC as our upper limit for ABC. Here 111. So 11 by 6. Now similarly, you just find front, so front, and then for back, and then left, first right and then left. So right and then left. See, this we already know, right? See, we are finding double integral over S F vector dot. So first you find S1 F dot n cap ds. This is S2 F dot n cap ds. This is S3 F dot n cap ds. This is S4 F dot n cap ds. And we already know, right, for front face your n cap will be I vector and your ds is dy dz. This will not change for any. And for back face your n cap is minus I vector and your ds is dy dz. And for right face your n cap is j vector and your ds is dx dz. If you have j, you don't write y component. And here your n cap is minus j vector and your ds is dx dz. We need to find up and down, that we'll do next slide. And you can see x is 1, y and z varies from 0 to 1. Y and z varies from 0 to 1. Here x is 0, y and z varies from 0 to 1. Yes or no? So you can see for the front face x is equal to 1 is fixed. For the front face x is 1 is fixed. Y varies from 0 to 1, z varies from 0 to 1. And for back face, x is equal to 0 is fixed because x is 0, x is 0, x is 0. Y and z are varying, and we know y and z varies from 0 to 1 only. And here y is equal to 1 is fixed, x and z varies from, see, after doing one problem itself, this problem seems to be comfortable for you. X z varies from 0 to 1, and here y is 0, x z varies from 0 to 1. Because both are x varies from 0 to 1, y varies from 0 to 1, z varies to 0 to 1 in the question. Here y is 0 is fixed. You can see the left face. So take the left face. This is left, right? So you can see y is 0, y is 0, y is 0, y is 0. X is varying, right? X is the one that is varying from, x varies from 0 to 1, z varies from 0 to 1. Now you can integrate this. So double integral over f vector dot n cap. So what is f dot n? We know f, right? So what is f? It is given in the question. So f vector is 2x minus z, 2x minus z I vector plus x square y j vector minus x z square is k vector. So f dot n cap. So f dot I. So it will be 2x minus z ds is dy dz. Y varies from 0 to 1, z varies from 0 to 1, and we know x is 1. So in 0 to 1, 0 to 1, 2 minus z dy dz. I'm just putting x to be equal to 1. So integration of 0 to 1. So integration of 2y minus zy 0 to 1 dz So integral of 0 to 1, 2 minus z dz. This will be 2 minus z square by 2. So 2 minus 1 by 2, right? Let's keep this as it is, 2 minus 1 by 2. Or you can write 4 minus 1 by 2, but let us keep this 2 minus 1 by 2 as it is. So here integration of f dot n cap. So n cap is minus I. So minus of 2x minus z dy dz. And we know x is 0. This term will be vanished. So 0 to 1, 0 to 1. So this will be integration of z dy dz. So integration of 0 to 1, z is constant, integration of dy is y varies from 0 to 1. So integration of z dz is z square by 2. So when you put upper and lower limit, you will have 1 by 2. And here this will be double integral over n cap f dot n cap. So dot j. So we will have x square y dx dz. X varies from 0 to 1, y varies. See, first we have x, so we need to put x limit, then you need to put z limits. But here everything is 0 to 1, so it doesn't make any problem here. So and we know y is 1, so this will be 1. So x square dx. So x square dx is x cube by 3. So we'll have 1 by 3 dz. Yes or no? Y will be 1, x squared is x cube by 3. So upper limit must be 1 by 3 dz. So 1 by 3 integration of dz is z. So 1 by 3 is your right hand surface. Now for left, double integral over s f dot n cap is minus j. So we'll have minus x square y. This will always be 0 because y is 0. Because y is 0. So 1 by 3 is your right. Now similarly, we need to find up and down. So up and down. So up surface, which is your s phi surface, double integral over s phi f vector dot n cap ds. And similarly, we will find down surface, which is s6, which is double integral over s6 f vector dot n cap ds. We already know, right? So n cap is k vector and ds is dx dy. And for up, your z is equal to 1. X and y varies from 0 to 1. Both are varying from 0 to 1. So I'm writing in single point. And here also your n cap will be minus k vector and your ds is dx dy and your z will be 0. X and y varies from 0 to 1. Both varies from 0 to 1. Both varies from 0 to 1. See, already explained, right? Why all this? So your n cap will be k, and you can see by the up, this is your up, right? 1, 1, 1, 1. Z is fixed, and you can see x varies from 0 to 1, y varies from 0 to 1. That is what I have written here. Whichever coordinate is fixed, you write that as fixed. Other you see vary. Now double integral over. Now what is f vector dot k? So f vector dot k. So it will be minus x z square. Minus x z square. Minus x z square dx dy, and x varies from 0 to 1, y varies from 0 to 1. So this will be, and we know z is 1. So we will have minus x dx dy. So this will be 0 to 1. X dx is x square by 2. This will be minus 1 by 2 dy. Again, this will be minus 1 by 2 is your upper surface integral. S6 f vector dot n cap. So f vector dot minus k cap will be minus of minus x z square dx dy. And you know z is 0, this full term will be 0. So therefore, double integral over s f vector dot n cap ds is same as double integral over s1, double integral over s2, double integral over s3, double integral over s4, double integral over s5, double integral over s6. So we have found all 6 surfaces. So 2 minus 1 by 2, 1 by 2. So this is 2 minus 1 by 2. This is 1 by 2. Yes, 3. 1 by 3, 0. 1 by 3, 0. This is minus 1 by 2 plus 0. Minus 1 by 2 plus 0. So these two will get cancelled. So we will have 2 plus 1 by 3 minus 1 by 2. This will be 6 plus 6 plus 1, 7 by 3 minus 1 by 2, 14 minus 3 by 6, so 11 by 6. So you can see from 1 and 2, so 2 is your surface integral, which is 11 by 6, and this 1 is your volume integral over del dot f. So from 1 and 2, Gauss divergence theorem is verified. Is it clear? So you can do problems on Gauss divergence theorem based on cuboid. Yes or no? From 1 and 2, Gauss divergence theorem is verified. So surface integral over unit normal vector is same as the triple integral over divergence of f. Is it clear? Yes. So we'll move on to next problem. See the two problems here we did on both are parallelepiped, right? Both are parallelepiped. This is the method for parallelepiped. So they will give the bounds for x, y, z. Just apply, find the vertices of all the sides. Then you can easily do. Right? Okay. Now we'll do one more problem, and then we will wind up. So we'll do one problem based on cylinder. Verify, verify Gauss divergence theorem. Verify Gauss divergence theorem for, so they are given f vector to be equal to y into I vector plus x into j vector plus z square k vector over the cylinder, over the cylinder. The previous problem it is cuboid or parallelepiped. Over the cylinder, cylindrical region. Cylindrical region, cylindrical region bounded by, a very interesting problem, bounded by x square plus y square is equal to 9, z is equal to 0, that is equal to 2. So we need to verify Gauss divergence theorem. That is, we need to show that the surface integral over f vector dot n cap ds is same as triple integral over v del dot f vector dv. Okay. Yes, so we have our x-axis, y-axis, and z-axis. Right? Let's call this as our x-axis. This is our y-axis. This is our z-axis. Right? Now we have a cylinder. We have a cylinder. So now the shape of cylinder, right? So cylinder will be, you have one curved surface area followed by a circle at the top and the bottom. So your total surface area will be curved surface area plus area of upper circle, area of lower circle. It's a very 9th standard level mathematics, right? So for cylinder, you will have this is the shape of cylinder. So this will be the curved surface area, and this area will, this is solid, right? Solid, we are talking about solid. So this will be the area of circle. This will, let us call this as R, call this as R radius to be R, I to be H. So for cylinder, curved surface area you will have plus the upper surface area, sorry, upper circle area, lower circle area. So total surface area will be curved surface area plus area of this circle plus area of this circle. Now we are not going to talk about that. Just remember the shape of cylinder. Okay. Now it is given that verify Gauss divergence theorem. So there is a vector field acting over that solid over the cylindrical region bounded by, see, x y. So x square plus y square is 9. That means that is what? It is a circle with the center 0 comma 0 and a radius r, right? The equation of circle is x minus h whole square plus y minus k whole square is equal to r square. So center is 0 comma 0 and the radius is 3. So in xy we have a, in xy we have a uh, sorry, in xy we have this, right? Ah, why they are filling, right? So we have in the xy it is bounded on this xy, right? So in the xy you have this circle which is x square plus y square is equal to 3 square. So you have a circle on this xy, right? Yes. And z varies from 0 to 2. So z is 0. See, imagine this is 3D. So this circle is on xy, z is 0, right? That is distance from, it is on z is 0. Z is 0 to 2. So you will have one more this also. The same circle I'm drawing in top. Same circle I'm drawing in top. So this is z is 0, z is 2. Right here, z is 0 and for this z is 2. So it is 2 units top of z. This is x square plus y square is equal to 3 square. This is center, radius is 3. Radius is 3. And we have a cylinder. Right. Now we need to verify Gauss divergence theorem for this. Now here for surface integral we have three surfaces here. For cube we have six surfaces, right? Left, right, up, down, front, back. Here we have three surfaces only, right? This upper surface, lower surface, and then this curved surface. So we have three surfaces to find a surface integral. Is it clear up to now? So we have this bottom surface, this upper surface, and this curved surface. Right? For cylinder, you can see this is a cylinder, right? So you have this curved surface, this bottom surface. This looks like hollow, but imagine this solid, right? Solid means it is filled with something. So this bottom surface, this top surface, and then this curved surface. So for finding surface integral, we will evaluate S1, S2, S3. But for cuboid, we will have S1, S2, S3, S4, S5, S6. But here we will evaluate three surfaces. And then first we will find volume, right? Volume integral is very easy. So first we will find volume integral. So we need to verify double integral over S, F vector dot n cap ds is same as triple integral over V del dot F vector dv. So del dot F is divergence of F. Now we will find RHS. So triple integral over V del dot F dV. Del dot F dV. So what is divergence of del dot F? So triple integral over V. So del dot F is nothing but differentiate this component with the dou by dou x of first component plus dou by dou y of second component plus dou by dou z of third component. This is your del dot F. This is what you will del dot F, right? So dou by dou x of this, dou by dou y of that, dou by dou z of that. Add it up. Now you can see this will be 0, this will be 0. So you will have only 2z. So this means I can take this 2 outside. So triple integral over z dx dy dz. Now we need to find the limits. We know z varies from 0 to 2, right? We know z varies from 0 to 2. Now we need to find, this is very easy, right? See, you can fix x, you can vary y, or you can fix y, you can vary x. You can fix x, you can vary y, or you can fix, see here, y varies from 0 to 3, right? Y varies from, y varies from minus 3 to 3. X varies from, so x is 3 square minus y square. So x varies from plus or minus root of 3 square minus y square. So y varies from 0 to 3. X varies from minus root of 3 square 3 square. Sorry, 3 square minus y square to plus square root of 3 square minus y square. Is it clear? See, you, or else you can also vary x also. See, here I'm varying y. Sorry, here I'm varying y. Here I'm varying y. Y varies from minus 3 to 3, and I'm keeping, you take x as a variable. You vary y from minus 3 to 3 because the radius is 3. You need to cover the full circle, right? Or you can take x as a variable. You can vary y, or you can take y as a variable and you can vary x. See, all these problems you already did in vector calculus, vector analysis, when we did some problems based on surface integral, volume integral, line integral. You can go through that video. This is the thing we need to find, right? Okay. So this is minus root of the 2. Okay. So integrate this. So this will be 2 times z varies from 0 to 2, y varies from, minus 3 to 3, y varies from minus 3 to 3. So z dx, z is constant. Integration of dx is x. Upper limit minus lower limit will be 2 times root of 3 square minus y square. Is it clear? Z is constant. Integration of dx is x. Upper limit minus lower limit will be this minus this. So it will be plus. So let us take this 2 outside now. So we will have 4 times. So this will be 4 times z varies from 0 to 2, y varies from minus 3 to 3. We will have z into root of 3 square minus y square, root of 3 square minus y square dy dz. Now integrate this with respect to y. There is some problem with the light, I think. Okay. So we know this formula, right? Integration of square root of a square minus x square dx. So we know this formula, right? Root of a square minus x square. So x by 2 root of a square minus x square plus a square by 2 sine inverse x by a. These are very standard formula that we come across in school level itself, right? Root of x by 2 root of a square minus x square. Now apply this formula. So 4 times integration of 0 to 2. Keep this z as it is. So integration of a square minus x square. So this will be y by 2 root of 3 square minus y square plus a square by 2. So a square by 2 sine inverse x by a. So y by 3. Is it clear? So minus 3 to 3 dz. Is it clear? See, just apply the formula directly. Instead of y, instead of x, we have y, and instead of a, we have 3. That's it. So apply upper limit and lower limit. So 4 times z varies from 0 to 2 z. Now upper limit is 3. So 3 by 2 root of 3 square minus 3 square plus 3 square by 2 sine inverse 3 by 3 minus lower limit. So lower limit is this thing, minus 3 by 2 root of 3 square plus minus 3 square, sorry, 3 square minus 3 square, 3 square by 2 sine inverse, or you can also take this even function also. So this will be 0, this will be 0. So you will have 4 times integration of 0 to 2 z. So this is z is common for both, right? Z is common for both, upper limit minus lower limit. So this will be 9 by 2. Sine inverse of 1 is pi by 2, right? Sine 90 is 1. So 90 will be sine inverse of 1. So sine inverse of 1 is pi by 2. And here upper limit minus lower limit, right? So here I have, here sine inverse of minus 1. This is minus pi by 2, right? So you will have minus minus will be plus. So you will have plus 9 by 2, 5 by 2. Is it clear? Tan inverse of 1 is pi by 2. This is minus pi by 2. So if you take minus out, it will be plus. So this will be 4 times. So 9 pi by 2 plus 9 pi by 2. So it will be 18 pi by 2, right? So 18 pi by 2, I can take that outside. We will have, we have dz left. So we have z dz. Z varies from 0 to 2. So this is same as, so 2 ones are, 2 twos are. So 36 pi z dz is z square by 2. Z varies from 0 to 2. So 36 pi 2 square is 4 by 2. Yes. So 9 pi 2 times 9 pi by 2. So which is 2 times 9 pi by 2 is 118 pi by 2. 2 ones are, 2 twos are. So 36 pi z square is 2, z square by 2. 2 square is 4. I think it is there any mistake you have made? Minus 3 to 3. Okay, okay. Actually, it is 2, right? Why have written 4? Sorry. No, no, no. I've taken this 2 outside, right? Just a minute. Okay, 4 times z into 4 times z into root of 4 times 0 to 2 root of, I think we are getting 72 pi, right? Is it clear? I made mistake anyway. It is we are getting 72 pi, right? Then the law 118 pi by 4 over the last. See, 9 pi plus 9 pi by 2. It is 18 pi by 2. That only, right? Just a minute, I'll check the question once again. Okay, okay. Actually, it is sorry 18 pi by 4. Sorry, 18 pi by 4 plus 18 pi by 9 pi by 4 plus 9 pi by 4. It is 18 pi by 4. Sorry, sorry. This will be 18 pi. So this will be 36 pi. So 36 pi is your. This will be 2. So 2 into 8 is 30. So 36 pi is our volume integral, right? 36 pi is our volume integral. Yes, thank you. Now we will find surface integral, right? Now let us call this as bottom, right? Call this as bottom. Let's call this as upper. Let's call this as curved surface. Just for understanding, right? Bottom, upper, and curved surface. Now let us try to evaluate double integral over S. Very important part. So double integral over S. F vector dot n cap ds is S1, S2, S3. So this is our bottom, this is our upper, this is our curved surface, right? Bottom, upper, curved surface. So now we will find S1. Now we will find double integral over S1 F vector dot n cap ds. Now we need to find ds, right? We need to find n cap, we need to find ds. This is the first step, right? We need to find n cap, we need to find ds, and then we need to find the limits also. For n cap, S1 is bottom surface, right? Now you can see this is our n cap for bottom surface. So our n cap is nothing but opposite of z. So n cap is minus k vector. Yes or no? N cap is minus k vector. And ds will be dx dy. I'll repeat. See, you have a cylinder, right? You have a cylinder like this, right? This is your bottom surface. So this is your perpendicular. This perpendicular is nothing but your z axis opposite of z in this direction. So n cap is minus k vector. You just visualize from this diagram. So visualize this as a tube cylinder, right? Here you have z, y. This is your unit vector. So which is opposite of z. So your n cap will be minus k vector. And here for this surface z is 0, right? Z is 0. For this surface z is 0. We need to find xy limits, right? We need to find xy limits. We know x varies from minus 3 to 3. You can keep y as a variable, or y varies from minus 3 to 3. You can keep x as a variable. That's your wish. Now you just find this. What is f dot n cap? Now what is your f vector? What is your f vector? So f vector is yi vector plus xj vector plus z square k vector. So your f dot minus k will be minus z square ds. This will be 0 because z is 0, right? You don't need to find the xy limit. It is time waste for you. Here you're going to put z is equal to 0 here, but here we have 0 into ds, which will be 0. So your s1 is 0. Now so we will find s2. Now we will find s2. Now double integral over s2 f vector dot n cap ds. Now we will find what is your n cap, what is your ds. So what is your z? Find x limits and y limits. Now n cap is same as what? N cap sorry z is sorry n cap is same as k vector. Yes or no? See, if you make a unit normal vector here, your n cap is minus k vector because it is opposite of z. But if you make a unit vector here, this is nothing but your z positive z axis. Yes or no? This is a unit vector that is perpendicular to this top because we are finding S2, right? S2 is your top surface. This is your S2, this is your S1, and this curved surface is S3. So for top, your n cap is nothing but k vector because that unit vector is parallel to z axis. So it is, if it is parallel to z axis, your n cap will be k vector, and z is 2 here. Yes or no? For this z is 2, for this z is 0. So your z will be 2. So ds is dx dy. So whenever you have k, you just put dx dy. Z is 2. X varies from, y varies from. So y varies from -3 to 3. X varies from minus root of 3 square minus y square to plus square root of 3 square minus y square. See, you can also keep x varies from -3 to 3. Y varies from root of 3 minus x square to 3 plus x square. So 3 square minus x square to 3 square plus x square. You can also do like that also. So therefore, this will be, now what is f vector dot n cap? So z square into k vector. So which is nothing but z square, uh, z square dx dy. X varies from minus root of 3 square minus y square to plus root of 3 square minus y square. Y varies from -3 to 3. See, we know z is 1. Sorry, z is 2. So it will be 2 square. So 2 square will be 4. So we will have 4 times double integral dx dy. Now you can see this is an even function, right? We have constant function, even function. So what I can do is, here we have minus root of 3 square minus y square minus root of 3 square minus y square minus 3 to 3. Let us multiply into 2 into 2, because I can write this as 0 to 3, 0 to root of 3 square minus y square dy dx dy. These are very simple, right? Properties of even function. So 2 times 0 2, 2 times 0 2. So 2 into 2, already we have 4. So that's it. You just have to integrate this. Dx dy, right? Now integration of dx is x. So this will be 4 2s are 8, 16, 0 to 3. So integration of dx is x. So this will be root of 3 square minus y square dy. Now again apply a square minus x square formula. This will be 16 times 16 times y by 2 root of y by 2 root of 3 square minus y square, y by 2 root of 3 square minus y square plus a square by 2 sin inverse x by a, sin inverse x by a. So 0 to 3. So when you put, this will be 0. When you put 3, this will be 16 into 9 by 2. Sin inverse of 1 is 5 by 2. So 2 ones are 2 eights are, 2 ones are 2 fours are. So you have got 36 pi. See, your upper surface is 36 pi, and we know the full volume is 36 pi. So that means your CSA has to be 0, yes or no? But we need to find it. See, we have found S1 and S2. So S1 area is 0, S2 is 36 pi. S3 obviously it has to be 0. Why? Because we know volume is 36 pi. Because the full volume is 36 pi. That 36 pi has to be equal to S1, S2, S3. S1 is 0, but in S2 itself we have got 26 pi. S3 surely has to be 0 only, but we need to evaluate that. Now we need to find S3. See, finding S3 is very, very important. Even though we know answer is going to be 0, but we need to do in some other way. Okay. Now to find S3. A very important part. Just understand this concept. S3 F vector dot n cap ds. Now we need to find n cap and ds. See, if you are, if this sub, you can see This you can see in this diagram. This curved surface lies on x as well as y as well as z. Everything is varying here. Yes or no? For this z is fixed, xy is varying. For this z is 0, xy is varying. But for this curved surface, all x, y, z are varying. If all x, y, z are varying, you have to follow the method which I am going to say to find n cap and ds. To find n cap and ds. Is it clear? Here z is fixed, xy is varying. Z is fixed, xy is varying. You can go by the previous methods. But in this curved surface area, all x, y, z are varying. In that case, you need to find n cap and ds using the formula. So what is n cap is, here S3 is a curved surface. S3 is a curved surface, curved surface here in which all x, y, z are varying. If that happens, what you do is n cap formula is del phi by modulus of del phi. Here, this formula is only using there also, but we are doing directly. N cap is del phi by modulus of del phi, where P is the surface which they are given, which is x square plus y square minus 9, right? Phi is the surface, right? What is the surface? Bottom surface. X square plus y square minus 9. That is the surface. Z is 0 to 2. You just take the phi to be the surface. Now, what is del phi? So, gradient of this. What is del? I into dou by dou x plus j into dou by dou y plus k into dou by dou z into phi. X square plus y square minus 9 divided by modulus of del phi, right? So del p is nothing but, so multiply this and differentiate. So it will be 2x I vector plus 2y j vector divided by modulus of 2x I vector 2y j vector. So del p is nothing but gradient of p. Now you know how to find gradient, right? So just apply gradient, that's it. So it will be 2x. So you just differentiate 2x multiply I, differentiate with respect to y, multiply j. So this is 2x I vector 2y j vector. This is your del p. By modulus of del p is root of 4x square plus 4y square. You know, right? Square root of xi plus yj is root of x square plus y square. So this is, if I take 2 outside, we will have xi plus yj divided by, so this is root of, so if I take 4 common, we will have x square plus y square, and we know x square plus y square is 9, right? Because that is a circle of radius 3. So we know x square plus y square is 9. So we know x square plus y square is 9. So substitute this 9 here. So this will be 4 nines are 36. So root 36 is 6. So 2 by 6 xi plus yj. So 1 by 3 xi plus yj is your n cap. Very, very important. If you want to find n cap for curved surface area in which all x, y, z are varying, n cap is del phi by mod del phi. Del phi is the surface they are given. So del phi is gradient of phi. Del dot something means divergence. If they don't dot means it is gradient, right? Okay, so you have found n cap. Now how to find ds? See, ds is the surface which you can choose any one of the three. When if you have seen my surface integral classes, you can either choose ds to be dx dy divided by modulus of n dot k. This is same as dy dz divided by modulus of n cap yz I xy yz dx dz divided by n cap j, n dot j. You can choose anything, right? You can choose anything. um, N cap, right? N cap, you can choose anything to be ds depending upon, if you have seen my surface integral, I would have we can choose anything, but if you choose something particular based on that problem, we can easily do that problem. I have said in that video, right? You can choose anything, but you need to choose accordingly so that your problem will get easier, right? Okay. Now you can choose anything to be ds here. Now I'm going to choose dx to be dx dy by n cap dot k. You can choose anything. After the class, you can try ds to be this and try to work out the problem with the same answer only. Let us choose ds to be, so choose dx to be dx dy divided by modulus of n cap dot k, right? Modulus of n cap dot k. Okay. Now, so we know ds, we know n cap. Let us try to make a dot product with f dot n cap and then ds. Now, what is f vector dot n cap? So, what is f vector? It is given in the question, right? Now, what is f vector? It is yi vector plus xj vector plus z square k vector dot n cap. So n cap is 1 by 3 xi vector plus yj vector. So make a dot product. This will be 1 by 3 uh, I. So it will be xy jj. It will be xy again. No, just multiply corresponding dot. That's it. So what you will have? What you will have? Uh, so it is 2xy by 3 is your f vector dot n cap, right? So xy plus xy by 3. So it will be 2xy by 3. Yes, 2xy by 3 is your f vector dot n cap. Now you need to multiply with, uh, okay. Now what will be this? This is dx dy divided by what is n cap dot k. This is your n cap. So n cap dot k. N cap dot k. So make a dot product with k vector. If you make a dot product with k vector, it will be 0, I think, right? What if you make a dot product with, see, we are finding n cap dot k. If you make a dot product with the n cap, this is your n cap. If you make a dot product with k, it will be 0, right? Okay. Then we will not take k. Then we will choose some other thing. We will choose. See, I'm choosing this. If I choose this n cap dot k, this is your n cap 1 by 3 xi plus yj. If you make a dot product with the k, it will be 0. So don't take this, right? What we will do is we will take n cap dot I. So dy dz divided by n cap dot I. So what is n cap dot I? If you make a dot product with I, so you will have x by 3. So this is 3 by x dy dz is your ds. Is it clear up to now? See, either you can choose n. Just a minute. Either you can choose ds to be this or this. If you choose this, n cap dot k will be 0. Don't do that. So if I choose n dot I, so n dot I is, you make a dot product with I, so we will have x by 3. So 3 by x dy dz. So therefore we are equipped with all. So S3 f vector dot n cap ds. This will be f vector dot n cap. So f vector dot n cap is 2xy by 3. ds is what? ds is 3 by x dy dz. 3 by x dy dz, right? And we know y varies from -3 to 3, z varies from 0 to 2. This is your S3 now. So 3 3 will get cancelled, x will get cancelled. So if I take this 2 outside, 0 to 2, -3 to 3, So we will have y into dy dz. So 2 times 0 to 2. This is y square by 2 minus 3 to 3 dz. So I can cancel this 2. This is integration of 0 to 2. 3 square is 9. Upper limit minus lower limit. So upper limit is 3 square minus lower limit, which is 0. So we have got this to be 0. Is it clear? Is it clear, right? See, that is an odd function. Y dy is odd function. So that will always be 0. That interval will always be 0. So therefore, double integral over S f vector dot n cap ds. See, to get 0, we are working a lot, right? You need to choose n cap ds. See, I repeat, n cap for curved surface. Curved surface. If everything is very, you choose n cap to be del phi by mod del phi, where phi is the surface. Phi is the surface, which is x square plus y square minus 9. Now this is very easy, right? So del phi is differentiate multiply I vector, differentiate multiply j vector, right? So you'll have 2x plus 2x I vector plus 2y j vector. You know how to find del phi, right? Del phi is the gradient of phi. We just have to multiply all this, multiply this I dou phi dou x, all this with all this with all this. You will get this 2xi plus 2yj. Okay. What you need to do is you need to take this term, multiply with I dou phi by dou x. So 2x dou by dou x of x square is 2x. These two will be 0 because dou by dou x of y square is 0, dou by dou x of 9 is 0. Similarly, you take this term, multiply with this. So j into dou by dou y of this is 0, dou by dou y of this is 2y, and so on. See, just go through my playlist on vector analysis if you know more about gradient. So we have found n cap using this, which is del phi by mod del phi. Del phi is 2xi vector, 2yj vector. So we have got this to be root of 4x square plus 4y square, and we know x square plus y square is 9, right? And we know x square plus y square is 9. So we will be getting this answer. Yes. Now, yes. So therefore, this area is, okay, I'll repeat. So n cap is using this formula. So we know n cap, right? So f dot n cap. Now you find f dot n cap. We know f is given the question. N cap we know. Both will be in terms of ijk only. So you'll get this as 2xy by 3. Now you can choose ds to be any one of these three. But don't choose one. If you choose one, n cap dot k will be 0. So don't choose this. So you can either choose this or this. If I choose this, n cap dot I will be, to make a dot with I, it will be x by 3. Right? It will be x by 3. So it will be 3 by x dy dz is for ds. Now apply that, you will get s3. So therefore, this is double integral over s1, s2, so s3 is a curved surface. So 0 plus 36 pi plus 0. So we will get this as 36 pi. So therefore, this causes as 2. So from 1 and 2, so from 1 and 2, Gauss, from 1 and 2, Gauss divergence theorem is verified. So in the next class, we will continue more problem based on this. So whenever you have a CSA, curved surface spot, make use of n cap ds using this idea, right? Yes. So that's it. So if you have any doubt, you can ask. Else we'll wind off. So in this class, we have started Gauss. We have seen 3 problems on Gauss divergence theorem, right? So the next class, we will continue more problems on that. If there any doubt, we will solve, or else we will wind off. Is any doubt? Yes. Thank you.